The 1950s were supposed to be the decade that railroads figured everything out. Diesel had won, steam was dying. The future was clear. All that remained was building the perfect diesel locomotive and watching profits roll in. Instead, every major builder and half the railroads in America produced machines so baffling, so poorly conceived, so spectacularly idiotic that historians still struggle to explain what anyone was thinking. These aren't the famous failures that show up in every railroad documentary. These are the obscure disasters that got buried in corporate archives because nobody wanted to admit they'd spent real money building them. 20 locomotives so stupid that seeing them for the first time makes you question whether the entire railroad industry suffered a collective brain injury in 1950. Number 1 is the Baldwin RF-16 Sharknose, and while some railroads got passable service from these units, the ones delivered to New York Central proved that Baldwin's quality control had completely collapsed by the early 1950s. NYC received their Sharknoses and immediately discovered that no two units were built to the same specification. Wiring harnesses were routed differently in every locomotive. Pipe fittings varied randomly between units. Components that should have been interchangeable weren't because Baldwin's shop forces assembled each locomotive as if they'd never built one before. Mechanics at NYC's Collinwood shops reported finding tools left inside sealed compartments, loose bolts rattling around electrical cabinets, and wiring connections held together with friction tape instead of proper terminals. The 608SC Prime Mover was Baldwin's own design, and it was an engine that seemed personally offended by the concept of sustained operation. Cylinder heads cracked with depressing regularity. The turbocharger mounting vibrated loose within the first 1,000 hours, creating oil leaks that turned the engine room into a slip hazard. NYC crews called them sharkbait because they consumed mechanics the way sharks consume fish, constantly, efficiently, and without mercy. By 1956, NYC was cannibalizing shark noses for parts to keep EMD units running, which tells you everything about how far Baldwin had fallen. Number 2 is a locomotive almost nobody has heard of. The General Electric 70-ton switcher built for industrial service, specifically the units delivered to a paper mill complex in Wisconsin in 1952. GE built these small switchers by the hundreds, and most worked fine. The Wisconsin units didn't. GE's Cummins engine option for this particular order arrived with a manufacturing defect in the cylinder block, casting that wasn't detected during quality inspection. Hairline cracks in the water jacket allowed coolant to seep into the oil system, creating a mayonnaise-like emulsion that destroyed every bearing in the engine within 300 operating hours. All 4 units failed within weeks of each other. The paper mill sued GE. GE blamed Cummins. Cummins blamed the foundry. The foundry blamed metallurgical testing procedures, while lawyers argued the paper mill had no locomotives and no way to move rail cars loaded with product. They hired a trucking company at 5 times the rail shipping cost and sent GE the bill. The units were eventually re-engined with different power plants, but the original disaster cost more in legal fees and lost productivity than the locomotives were worth. Number 3 is the Fairbanks Morse H1666 Trainmaster, which was simultaneously the most powerful single-engine road switcher of the 1950s and one of the dumbest things ever put on rails. The Trainmaster produced 2,400 horsepower from a single opposed piston engine at a time when competing units maxed out at 1,750. On paper, this was dominance. In reality, it was a maintenance catastrophe, wrapped in a car body and set loose on an unsuspecting railroad. The opposed piston engine had 2 crankshafts connected by timing gears. When those gears wore, and they wore constantly because the forces involved were enormous, piston timing drifted. When timing drifted, pistons got uncomfortably close to each other inside the cylinder. When pistons got too close, they collided. When pistons collided, the engine turned into a very expensive collection of scrap metal. Southern Railway purchased Trainmasters and assigned them to their toughest Appalachian grades, reasoning that 2,400 horsepower in a single unit would eliminate the need for multiple unit operations. What they got was 2,400 horsepower for about 600 hours between catastrophic engine failures. Mechanics who worked on trainmasters developed a 1,000-yard stare normally associated with combat veterans. The opposed piston engine required tools and techniques that no other locomotive used. Parts were unique to FM and delivered on FM's schedule, which bore no relationship to when the railroad actually needed them. Southern eventually traded their entire trainmaster fleet for EMD-GP9S at a financial loss and considered it a bargain. Number 4 is something you've genuinely never seen because almost no photographs exist. In 1953, the Kansas City Southern Railway's mechanical department decided they could convert surplus Alco S1 switches into road units by mounting 2 of them back-to-back on a single frame with a fuel tank between them. The result looked like someone had welded 2 locomotives together after a head-on collision. The electrical systems were incompatible because the 2 donor units came from different production runs. KCS electricians spent months trying to make the control systems talk to each other. When they finally succeeded, the combined unit produced power surges that blew main fuses approximately every 45 minutes of operation. The frame connecting the 2 units flexed on curves in ways the designers hadn't anticipated, cracking welds and misaligning the driveshaft connections. Each engine ran at slightly different temperatures because the shared cooling system favored whichever end was facing into the wind. The downwind engine overheated chronically. KCS operated this Franken locomotive for approximately 18 months before cutting it apart and returning the components to their original configurations. Mechanics celebrated with a barbecue. Number 5 is the Westinghouse gas turbine locomotive built for the Union Pacific in 1951, specifically the second prototype that was supposed to fix all the problems of the first. It fixed none of them and added new ones. The turbine's fuel control system used a mechanical governor that responded to load changes with all the agility of a sleeping elephant. When the locomotive crested a grade and the load suddenly decreased, the governor took nearly 30 seconds to reduce fuel flow. During those 30 seconds, the turbine overspeed protection would trip, shutting down the entire power plant and leaving the locomotive coasting without power until the crew could restart. On undulating terrain, the turbine tripped and restarted so frequently that crews referred to the operating procedure as yo-yo railroading. The exhaust system directed superheated gases downward between the trucks. This worked fine in winter. In summer, the exhaust temperature was sufficient to ignite creosote-treated wooden ties beneath the locomotive when stopped at signals. UP crews learned to never stop on wooden tie track with the turbine running. Since most of UP's track used wooden ties, this presented an obvious problem. The locomotive was returned to Westinghouse in 1954, and nobody asked for it back. Number 6 is the Plymouth ML8 diesel switcher, a small industrial locomotive that was engineered with what can only be described as aggressive indifference to the people who would operate it. The cab was designed by someone who apparently believed locomotive engineers were 2-dimensional beings. Seat-to-ceiling height was 48 inches. The control stand was positioned so that operating the throttle required the engineer to twist their torso 90 degrees to the left while simultaneously pressing foot pedals located 18 inches to the right. Window placement provided excellent visibility of the sky directly overhead and virtually nothing at ground level where the tracks and workers actually were. Ventilation consisted of a single vent that, through some achievement of anti-engineering, drew exhaust fumes from the engine compartment directly into the cab. Operating a Plymouth ML8 in summer was like working inside a very slow, very hot oven that was also trying to poison you. Industrial railroads bought them because they were cheap. They regretted it because the crews they assigned to them filed grievances with such volume and creativity that labor relations departments started keeping ML8 complaint files in their own dedicated cabinets. Number 7 is the Alco RS3, delivered to the Lehigh and Hudson River Railway in 1952. And while the RS3 was generally a capable locomotive, these specific units demonstrated what happens when a railroad specifies custom modifications without understanding the consequences. L and HR requested that Alco install a steam generator for passenger heating in a locomotive designed for freight service. Alco complied by wedging a steam generator into the engine compartment, in a location that blocked access to the number 4 and 5 cylinder banks of the 244 engine. Performing a routine valve adjustment on those cylinders required removing the steam generator first, a job that consumed an entire shift. The steam generator's water tank reduced fuel capacity by 400 gallons, limiting the locomotive's range. The exhaust from the steam generator was vented through the carbody roof at a point directly above the dynamic brake resistor grids. When the locomotive operated in dynamic braking, while the steam generator was running, the combined heat warped the resistor grid housing. L and HR operated these modified RS3s for their entire service lives because they couldn't afford replacements, but every mechanic who worked on them considered them proof that God had a sense of humor. Number 8 is a locomotive that technically never received a proper designation. In 1954, the Chicago Great Western Railway attempted to rebuild an aging EMD-FT unit by replacing the original 567 engine with a surplus marine diesel acquired from a Navy disposal sale. The marine engine produced adequate horsepower, but was designed to operate at constant speed, driving a ship's propeller. Railroad service demands constant speed changes. The marine engine's fuel injection system couldn't handle the rapid load transitions and responded to throttle changes by producing enormous clouds of black smoke, followed by either a surge of power or a complete stall. The engine cooling system was designed for seawater and couldn't maintain proper temperatures with the freshwater radiator system CGW installed. The marine engine also weighed 4,000 pounds more than the original 567, shifting the locomotive's center of gravity high enough that it developed an alarming lateral roll on curves. CGW operated this conversion for approximately 7 months before parking it behind their Allwine, Iowa shops, where it sat deteriorating for 3 years before being scrapped. The total cost of the conversion exceeded the price of a new GP9, a fact that CGW's mechanical superintendent reportedly learned on the same day he tendered his resignation. Number 9 is the Lima Hamilton 1,200 horsepower transfer switcher, and it earns its place on this list through sheer mechanical spite. Lima Hamilton built these units in the early 1950s during their desperate final attempt to compete in the diesel market. The Hamilton engine was designed by engineers who had extensive experience building stationary power plants and apparently believed that a locomotive was just a stationary power plant that happened to move. The engine mounting system used rigid bolts instead of flexible mounts. Every vibration from the engine transmitted directly into the frame, which transmitted it into every component attached to the frame, which was everything. Electrical connections vibrated apart. Pipe fittings loosened. Gauge glasses cracked. The cab shook so violently that crews reported difficulty reading the instrument panel. After extended operation, engineers complained of blurred vision and numbness in their hands, symptoms consistent with whole-body vibration exposure that wouldn't be regulated for another 30 years. The air compressor, mounted directly to the engine block, vibrated in harmony with the main engine at certain RPM ranges, creating a resonance that produced a howling noise audible half a mile away. Railroads nicknamed them "screaming lemurs" and retired them at the earliest possible opportunity. Not a single one was preserved because nobody wanted to remember them. Number 10 is a creation so inexplicable that researching it feels like reading fiction. In 1955, the Duluth, Missoub, and Iron Range Railway purchased a small fleet of Whitcomb diesel switchers for ore dock service. Whitcomb was a reputable builder of small industrial locomotives. These units were not reputable. The Whitcomb design placed the radiator directly behind the cab with no firewall between them. When the radiator developed a leak, which happened regularly because ore dust clogged the fins and caused overheating, superheated coolant sprayed directly into the back of the engineer's seat. 2 engineers suffered burns before DM and IR installed improvised sheet metal shields. The exhaust system routed through the frame members, heating the walkways to temperatures that melted the rubber soles of crew boots. The fuel tank was positioned so that the fill port was directly beneath the exhaust outlet, refueling while the engine was running, which was standard procedure for switches that operated around the clock, meant pouring diesel fuel past a surface hot enough to ignite it DM and IR's safety department eventually mandated a full engine shutdown for refueling, adding 20 minutes to every fueling stop. The locomotives functioned, barely, for about a decade before being replaced by units designed by people who apparently had actually seen a railroad before. Number 11 is the Baldwin AS616, and while Baldwin built several acceptable locomotive models in their final years, the AS616 wasn't one of them. This 6-axle road switcher used Baldwin's 608A engine, which combined the power output of a modern design with the reliability of a hand grenade. The 608A used a unique combustion chamber design that created hotspots in the cylinder heads. These hotspots caused pre-ignition that cracked pistons with metronomic regularity. Railroad shops ordered replacement pistons by the crate rather than individually. The turbocharger was positioned in a location accessible only by removing half the engine room roof panels, a job requiring 4 mechanics and a crane. Turbocharger failures occurred approximately every 2,000 hours. Each replacement consumed 2 full days. The trucks used a span bolster design that wore pivot pins at 3 times the rate of comparable EMD or Alco trucks. When pivot pins wore beyond limits, the truck would occasionally bind on sharp curves, producing a grinding shriek and lateral forces sufficient to shove ballast off the roadbed. Railroads that bought AS616s universally traded them away at the first opportunity, often accepting 10 cents on the dollar just to eliminate the maintenance burden. Number 12 is the EMD LWT-12, a lightweight train power car that EMD built for the Aero train, and it might be the dumbest idea to come out of LaGrange, Illinois in the entire decade. EMD took a standard GM bus body, mounted it on modified locomotive trucks, and installed a 1,200 horsepower 567C engine inside. The bus body provided no structural strength, so EMD added a separate underframe that added weight, defeating the entire lightweight concept. The power car rode so roughly at speed that dishes flew off tables in the dining car, and passengers reported motion sickness. The bus body's thin walls provided almost no sound insulation from the engine directly beneath the crew compartment. Engineers wore ear protection and still complained of hearing damage. The coupling between the power car and the lightweight passenger cars transmitted every vibration and lurch amplified through the train. Both Pennsylvania Railroad and Union Pacific tested the Aero train, and both rejected it with language that was diplomatically unflattering. GM had built the Aero train primarily as a publicity vehicle to promote highway bus technology as the future of rail travel, which tells you everything about how seriously they took the railroad application. The surviving Aero train power car sits in a museum, which is exactly where it belonged from the day it was built. Number 13 is something the Norfolk and Western Railway would prefer you never learned about. In 1953, N&W's famously competent mechanical department attempted to convert a Class A articulated steam locomotive to burn oil instead of coal. N&W was a coal-hauling railroad. They burned their own product in their own locomotives. The oil conversion experiment was driven by a single operating officer who believed oil firing would reduce locomotive servicing time. He was right about that. He was wrong about everything else. The oil conversion required removing the mechanical stoker and installing oil burners, pumps, heaters, and a modified tender. The modifications cost more than a new diesel locomotive. The oil-fired Class A produced 15% less steam than the coal-fired version because the firebox geometry was optimized for coal combustion, not oil. Flame impingement from the oil burners damaged firebox sheets within 200 operating hours. The oil heating system failed in cold weather, causing fuel to gel in the lines. Most embarrassingly, N&W had to purchase oil from competitors because they were a coal company. Operating department memos from the period reveal increasingly creative profanity directed at the officer who proposed the experiment. The locomotive was converted back to coal within 6 months, and the proposing officer was transferred to a position where his future ideas would cause less damage. Number 14 is the General Electric 44-ton switcher built for a logging railroad in Oregon in 1953, and it illustrates what happens when a locomotive meets an environment it was never designed for. GE's 44-tonners were designed for light industrial switching on relatively flat, well-maintained track. Oregon logging railroads operated on temporary track laid directly on forest soil, with grades exceeding 6% and curves tighter than anything a mainline locomotive would ever encounter. The logging railroad specified the 44-tonner because its lightweight wouldn't destroy their temporary track. GE obliged without apparently asking what kind of track they meant. The first unit sent into the woods derailed on its second day when temporary track shifted under its weight. The cooling system clogged with sawdust and bark within hours of entering the logging area. Pine sap coated every external surface and worked its way into electrical cabinets, causing short circuits that defied diagnosis because the insulating properties of dried sap created intermittent faults. The locomotive's two small Cummins engines couldn't produce enough power for the grades and loads the logging operation demanded, so crews routinely overloaded both engines until they overheated. The logging railroad went through 6 complete engine replacements in 3 years before finally purchasing a used steam locomotive that handled the conditions without complaint. Number 15 is the Budd RDC-2 rail diesel car, delivered to the Boston and Maine Railroad in 1953. The RDC concept was sound and many railroads operated them successfully. B&M's experience was not successful. Their units were assigned to routes with station platforms of varying heights, requiring passengers to navigate steps of inconsistent depth. The underfloor engine placement meant the passenger compartment floor was higher than conventional coaches, creating a step-up that elderly and disabled passengers couldn't manage without assistance. The 2 Detroit diesel 6110 engines mounted beneath the floor produced vibration that traveled through the car structure and manifested as a persistent buzzing in every seat. Passengers described it as sitting on a giant electric razor. The heating system drew warmth from engine coolant, which meant heat was unavailable until the engines reached operating temperature, which took 30 minutes in winter. For the first 30 minutes of every morning trip, passengers sat in a freezing car listening to diesel engines vibrating their fillings loose. The transmission failed with such regularity that B&M maintained a dedicated RDC transmission rebuild shop. When transmissions failed en route, the car could limp along on its remaining engine at reduced speed, turning a 45-minute commute into a 90-minute ordeal. Commuters wrote letters to newspapers. Newspapers wrote editorials. Politicians wrote to B&M. B&M wrote checks for repairs. Number 16 is a locomotive that the Southern Pacific Railroad built in their own Sacramento shops in 1951, and it demonstrates why railroads should leave locomotive building to locomotive builders. SP's mechanical department decided to create a slug unit, an unpowered locomotive body containing only traction motors, powered by electrical cable from an adjacent diesel unit. The concept was sound. SP's execution was not. They used a retired steam locomotive tender frame as the basis, mounting surplus traction motors on trucks salvaged from a scrapped EMDF unit. The tender frame was not designed to handle the torque reactions from traction motors. Welds cracked within the first month. SP reinforced the frame, adding so much steel that the slug weighed more than the powered unit feeding it electricity. The combined consist now exceeded track weight limits on half the yard tracks it was supposed to serve. The electrical connections between the slug and its mother unit used surplus military cable connectors that corroded in Sacramento's climate. Power surges from intermittent connections burned out traction motors at a rate that consumed SP's entire surplus motor inventory within a year. The slug was quietly retired in 1954, and its frame was returned to its highest calling, being scrapped. Number 17 is the American Locomotive Company's DL600, sold to a handful of export customers and one ambitious domestic short line in 1954. The DL600 used Alco's new 251 engine, which was actually a decent power plant that would go on to have a successful career. The problem was everything else. Alco's electrical system used components sourced from 3 different suppliers because no single supplier would commit to Alco's aggressive delivery schedule. GE generators were connected to Westinghouse control systems, driving Alco-designed traction motors. When this electrical United Nations had to work together under load, the results were unpredictable. Control sequences that worked perfectly on the test stand produced erratic behavior in service. The transition from series to parallel motor connection caused power surges that tripped protective relays randomly. Mechanics couldn't troubleshoot effectively because the diagnostic procedures for each supplier's components contradicted each other. When the railroad called GE for help, GE blamed the Westinghouse controls. When they called Westinghouse, Westinghouse blamed the GE generator. When they called Alco, Alco blamed both suppliers and then stopped returning calls. Number 18 is a creation of the Chicago, Burlington, and Quincy Railroads Mechanical Department in 1956. CB&Q decided to convert a retired EMDE-5 passenger unit into a track geometry measurement car by removing one prime mover and installing measurement equipment. The conversion itself was competent. The stupidity was operational. CB&Q assigned the converted unit to measure track geometry while being propelled backward by a freight locomotive at speeds up to 60 miles per hour. The E5 cab, designed for forward operation, provided zero visibility when running backward because the only rear-facing windows were small portholes in the engine room bulkhead. The crew operating measurement equipment couldn't see what was ahead of them. They relied entirely on radio communication with the pushing locomotive's crew, who could see ahead but couldn't read the measurement instruments. When radio communication failed during one test run, which it did, because 1950s portable radios failed constantly, the measurement car was pushed through a work zone at 55 miles per hour. Nobody was injured by pure luck. The Federal Railroad Administration later cited this operation as an example of why regulations governing measurement equipment operations were necessary. CB&Q modified the car to operate in the correct direction, which should have been the plan from the beginning. Number 19 is the Electromotive Division's experimental SD7M, a modified SD7 that EMD built in 1953 to test an automatic engine management system. The concept was ahead of its time. The execution was ahead of the available technology. The SD7M used a primitive analog computer to optimize engine performance by automatically adjusting fuel injection timing, turbocharger wastegate position, and cooling fan speed based on sensor inputs. The sensors were 1950s technology, which meant they were large, fragile, temperature sensitive, and prone to drift. Within 100 hours of operation, sensor calibration had drifted so far that the computer was making adjustments based on fictional data. Fuel injection timing shifted to a setting that produced maximum smoke and minimum power. The turbocharger wastegate stuck fully open, reducing boost pressure to nothing. Cooling fans ran at maximum speed regardless of temperature, wasting horsepower and creating a wind tunnel effect in the engine room that blew loose paper and debris into electrical cabinets. EMD engineers attempted to recalibrate the system monthly. Each recalibration lasted approximately a week before sensor drift made the computer's decisions worse than random chance. The test locomotive was quietly returned to standard SD7 configuration in 1955, and EMD didn't attempt computerized engine management again until electronics technology caught up with the concept 2 decades later. Number 20 is perhaps the most poetic failure of the entire decade. In 1957, the Reading Railroad commissioned a custom-painted EMDGP-9 in a special livery celebrating the railroad's centennial. The locomotive was mechanically standard in every respect. The stupidity was entirely aesthetic. Reading's marketing department specified a paint scheme that used 7 different colors, including metallic gold, requiring 14 separate masking and painting steps. The paint job cost more than the locomotive's first annual maintenance budget. The metallic gold paint, sourced from an automotive supplier, was not formulated for railroad service. It began peeling within 3 months of exposure to diesel exhaust, coal dust, and the general filth of railroad operations. Reading's shops attempted touch-up painting, but the automotive gold couldn't be matched with industrial paint, creating visible patches that made the locomotive look diseased. Within a year, the Centennial locomotive was so visually degraded that Reading's own public relations department requested it be repainted in standard colors to stop the embarrassment. The locomotive was quietly repainted in standard green and yellow, the 7-color Centennial scheme having survived approximately 11 months. The marketing department that commissioned the paint scheme reportedly was not consulted on future locomotive aesthetics. These 20 locomotives represent the 1950s railroad industry at its most confused, desperate, and occasionally delusional. Everyone was built or modified by people who should have known better, funded by organizations that couldn't afford the waste, and operated by crews who deserved better equipment. The decade that was supposed to bring clarity to American railroading instead produced a museum of bad ideas, failed conversions, impossible specifications, and engineering hubris that burned through millions of dollars, while producing nothing but maintenance headaches and entertaining stories for future generations. The locomotives you've never seen before were hidden for good reason. They represent the industry's most embarrassing moments, the decisions nobody wanted to explain, and the machines nobody wanted to photograph. Now, you've seen them, and you understand why they were buried. Some things deserve to be forgotten. These locomotives earned their obscurity the hard way. Don't forget to subscribe so you don't miss future updates. Here's another video I've specially selected for you.